Okay, we're going to talk about using the Jordan Curve Theorem. All right, so the JCT, Jordan Curve Theorem. Right, this is going to be really a powerful tool for reasoning about the faces in a planar graph. And for really everything we do with planar graphs, at some point it's going to get back to the Jordan Curve Theorem because it captures most of what we care about in terms of the important structure that's special about the plane. And we're going to build up some other tools on top of it so we don't have to continuously invoke the Jordan Curve Theorem directly. But you should remember that it's under the hood when we're using other more elaborate tools. All right, so just a couple exercises that you might work on your own. I'm going to state them and I'll leave them for a second to think about. The first one is if you have a graph that has 4 vertices, and it has some C3 subgraph. You know, C3 is also K3, so it's a triangle. And I may just sometimes call this a triangle subgraph, even though triangle usually means you should think geometry. I'm just talking about a subgraph that's a cycle with 3 edges, 3 vertices. And the claim is that every embedding of that graph, so you take this graph with just 4 vertices, every embedding of it, that cycle, that 3-vertex cycle, the triangle, is the boundary of a face. So there's no way to take that cycle if the graph only has 4 vertices and put the 4th vertex and the rest of the graph somewhere that's going to cause this to not be a face. And the intuition, I think, is that it either has to be inside or outside. Right, so if it's inside, then that triangle is the outer face. And if it's outside, that triangle, the inside of the triangle is a face. And you can prove this by the Jordan Curve Theorem. It's really just invoking the fact that the embedding of the cycle is a polygon and therefore, well, all right, piecewise linear embedding of the cycle is a polygon. And so there's an inside and an outside. And so that 4th vertex has to lie either all inside or all outside, and the edges as well. That edge is coming out of that 4th vertex. All right, so that's the first one. And very similarly is kind of the downside of this, or the more negative result, which is that if you can actually come up with, and I encourage you to play with this a little bit, is to find a 5-vertex planar graph and with a cycle in it, and really a C3, a 3 cycle, where there doesn't exist any embedding where that cycle bounds a face. So even though that triangle is in the graph, it somehow never shows up as the face in the embedding, even though there are embeddings. Right? It is a planar graph. Just being a triangle in a graph doesn't guarantee that you're going to be the boundary of a face. Now, this is also a good opportunity for me to mention something, which is that in terms of how we talk about graphs, once we start talking about planar graphs and embeddings of planar graphs, it's very tempting, and I'm going to do this by accident and sometimes maybe even just on purpose, is to talk about the embedding and the graph as being the same thing. So here's what I mean. If we have an embedding of a graph and I talk about the edge in the plane, you should know that I mean where that edge got embedded as a curve in the plane. Sometimes I may talk about the vertices as if they're points in the plane, and I may talk about the edges as if they're just curves in the plane. And I hope that in the context of what I'm saying, it should always be clear. We'll see. You'll let me know if it gets confusing. All right. Here's a definition that we can use, and this will give us an interesting class of graphs, which are interesting in their own right, but they're also interesting for us now to talk about ways of using the Jordan Curve Theorem to prove some interesting stuff. So the graph is outer planar if there's some embedding that places all the vertices on the outer face. Right, so that face that goes off to infinity, that piece of the plane that gets arbitrarily far away. And here are a couple examples. Oh, I missed one edge here. I was going to call this a triangulated polygon. Now I think it's a triangulated polygon. And this other example here is a tree. All right, so in this case, the outer face really is bounded by a cycle. Here, the edges that are on the outer face are really all the edges of the graph, which is one of the properties of a tree. So these are two examples where every vertex is on the outer face. Another way to think of being on the outer face is to say, well, that I can go from any vertex and I can find a path that doesn't touch the embedding and it gets all the way out to infinity. Right? I'm somehow never boxed in. One of the first things you might prove about planar graphs, or outer planar graphs, is that this graph K4, the complete graph on 4 vertices, is not outer planar. The way you would prove that is you start by observing, well, K4 has 4 C3 subgraphs. It has only 4 vertices. Remember we just said that 4 vertex graphs, if it has a C3 subgraph, each one of these triangles actually has to be a face. It has to bound a face, that is, in the embedding. Right, so each bounds a face. Let me also just highlight something important here, which is that you can draw a planar embedding of a graph, K4. So here's K4. And you can observe that in this particular embedding, not all of the faces, not all of the vertices are on the outer face. So now I'm in the rather difficult situation of trying to reason about all possible piecewise linear embeddings of this graph. So finding one example really doesn't do it, but it can give us some intuition. And you'll notice that as I was drawing this, well, I started with this one outer face here, and I put the last vertex on the inside. If I put it on the outside, I encourage you to play this game and see if you can try to put all the vertices on the outside, and you'll always get stuck. So let's label these vertices 0, 1, 2, 3. And if you recall, because in the neighborhood of an edge, right, in the neighborhood of an edge there's just 2 sides, and we can walk along an edge. So if I'm on point on one side, I can walk along the edge and I can find paths along the whole edge. What that means is that each edge can participate in only 2 faces, only 2 path-connected components, one for each side here. So let's pick a particular edge. Let's say that this was an edge 0, 1. I drew it as a straight line, but it could have been some polygonal paths. So edge 0, 1 has to be on the boundary of at most two different faces. Oops, the boundary, BDY, short abbreviation for boundary, must be on the boundary. But it has to also be on the boundary, not just of at most 2 faces, but we know 2 faces that it is on the boundary of. It has to be on the boundary of triangles, what are they? 0, 1, 2, which is this one, and 0, 1, 3, which was this one. Okay, so I know this particular edge, I know which faces it must be on. But now the same argument holds for every single edge, right? So every edge, all 6 of the edges in K4 appears in 2 triangles. But that's all the edges. There aren't any left. And so if there was an outer face that contained all the vertices, it doesn't have any edges, which is going to be a contradiction, right? Because it's not possible for me to go from out to, let's say, outside on the outer face and not reach any edges at all. So if there was the outer face with 4 vertices, then it doesn't have any edges, which is impossible. right? Every edge is already used up its allotted two faces that it can participate in. You can't find such an embedding where K4 has all the vertices on the outer face. You always have one vertex that's inside a triangle formed by the other three. There's another graph here. It's important for outer planarity. It's K23. Remember, this is the complete bipartite graph on 2 and 3 vertices. The nicer way to draw this one, I think, is this way. Right? Rather than drawing the second one over here, let's draw it over here. What's nice here, of course, is that we see this is obviously now a planar graph. And you can also see where you get into the same kind of trouble when attempting to draw it as an outer planar graph. Right? It's planar, I can draw it without crossings, but it's not outer planar, which would be drawing it so that all these vertices were on the outer face. And so if I want to prove this, suppose there did exist such an embedding. I should be careful what I mean here, embedding with all vertices on the outer face. Well, each one of these C4 subgraphs, right? So let's just take one for example right here. Right, there's a subgraph here, which is a cycle of 4 vertices, actually has to bound a face. And the argument here is the same as we said for four vertex graphs with a triangle. You see we've got there are 3 C4 subgraphs, and each one there's only one other vertex, so that vertex has to be either inside or outside. If it's outside, then the interior is a face. If it's inside, then the exterior is a face. So one side or another, it's going to bound a face. And there are 3 of these C4 subgraphs. So as before, I'll just write as before, you can work through the same kind of logic that we did before with the K4, then you're going to see that every edge is in 2 C4 subgraphs, which means that it's already incident to 2 different faces. And so there are no edges left to bound the outer face. Because the outer face can't just be a C4 subgraph, right? Because it has 5 vertices. All right, K4 and K23, nice examples of graphs that are not outer planar. In fact, they're really the examples of graphs that are not outer planar. They're the canonical examples, and we'll prove that in a sec. But first, let's observe something else about outer planar graphs and subdivision. We don't have to show this just yet. Let me just focus on the statement. If I have a graph, G, and it's a subdivision of H, and G is outer planar, then H is outer planar. Okay, this should be kind of intuitive. I think the idea, hopefully, if you think about it a little bit, you'll say, well, if G is outer planar, you just take the embedding, and if H is a subdivision of it, then you can get an embedding of H that sits right on top of G and has all the vertices still on the outer face. To make it just a smidge more formal, you might actually give a name to that embedding of G. So phi is some embedding of that graph. Technically, right, it's a mapping from the geometric realization of G into the plane. And if it's an embedding that puts all the vertices on the outer face, then because I think we showed this, right, if you have a graph that's a subdivision of another graph, then their geometric realizations are homeomorphic. Okay, so if I take the embedding and I just look at where it puts the vertices of H, well, that has to be a subset of the vertices of G. And so if I take the composition of the embedding and the homeomorphism, I'm going to get an embedding of H, and all those vertices are still on the outer face, right? Because this embedding is going to have the same image as just the embedding phi, right? So this maybe it helps to remember that when we do this kind of subdivision, and you say I had a graph like this, and I just subdivided a couple edges. I subdivided it here, here, and here. That I can find an embedding, which is exactly the same, right? So it's just, right, by just composing with the homeomorphism, it sits right on top here. All right, so that actually gives me the embedding of H with all the vertices on the outer face. And so that proves that H is outer planar, right? It's proven just by explicitly giving the embedding, constructing it straight from the embedding of G. All right, so now, in fact, we're ready to show this stronger statement, which is that a graph is outer planar if and only if it has no K4 or K23 topological minors. Again, that's equivalent to saying that there's no subgraph that's a subdivision of K23 or K4. So we started out with these two examples, and it turns out, in a way, they're the only two examples that matter. If you came up with another example of an outer planar or graph that was not outer planar, then you would find K4 or K23 hidden somewhere inside it. So here's the idea. We already know that K4 and K23 are not outer planar. And we know that if they're not outer planar, then the subdivisions are still not outer planar. Just prove that one. So if it has a K4 or K23 topological minor, then it's definitely not outer planar. So K4 or K23 topological minor implies not outer planar. So what about in the other direction? In the other direction, it's quite a bit trickier, because we need to show that every graph that's not outer planar has one of these topological minors. Let's do that now. Okay, so this is my claim. I claim that if there's no K4 or K23 topological minor, then the graph is outer planar. If it's not outer planar, then you take the embedding that maximizes the number of vertices on the outer face. Okay, so you want as many vertices as possible on the outer face. And then, since it's not going to have all of the vertices on the outer face, we know that there has to be some cycle that contains some vertices. So if you look at the vertices and the part of the graph that landed inside some cycle, there's a couple cases to consider. One is where if I can find a vertex that's only connected to, say, one vertex on the cycle. Well, that means it wasn't maximal, because I could have taken this part of the graph and brought it out to the other side. And I would have had at least one more vertex on the outer face. Another case is if I find a vertex with three different paths to the cycle. Well, you'll notice here, this means that there must have been a K4 topological minor. You can imagine just taking the, say, a spanning tree of the graph induced on the vertices inside the cycle plus maybe on the cycle. And if you can find three different paths, right, there's going to be some vertex that has degree more than 2, otherwise you would just have paths. And so you take that vertex, you take these paths, and then the cycle itself combine to give you a K4 topological minor. All right. In the last case, again, this is just sort of a sketch, but this is the main idea, that if you only can find your way to 2 different spots, right, you have a vertex inside, and you can put paths from that vertex to 2 different vertices on the cycle. Well, if you can't move that vertex to the outside and increase the number of vertices on the outer face, then it must be that there were vertices on this path. Okay, so in this case, you'll notice what I've drawn now. I have K, 2, 3. Right? So this edge, sorry, don't be too confused, right? This edge is the same as this one. I just moved it over here. The original graph then had this K23. Right? Here's the 2, here's the 3. And so I found my topological minors hiding in there just by assuming that the graph was not outer planar, just knowing that because it was not outer planar, that when I take the embedding, there's some cycle, and by the Jordan Curve Theorem, there's a vertex inside that now can't find a path outside. And just by looking at how those vertices connect up to the cycle, I get one of these cases, one where it just wasn't maximal, so I get rid of that by assumption, and then these are the other 2 cases. If I had 4, it would be no big deal. I could throw one of them out. That's the kind of main way to characterize the outer planar graphs in terms of forbidden topological minors. So here's a quick summary here, is that the Jordan Curve Theorem really helps us to reason about faces in the graph. So once you have an embedding of a graph, suddenly you have faces. You have more structure than just vertices and edges. You suddenly have these 2-dimensional things. And these 2 graphs, K4 and K23, these are not outer planar. And in fact, a graph G is outer planar if and only if it does not have K4 or K23 topological minors.